Unlike a cinematic film or pre-rendered digital animation sequence, a video game cannot simply sit back, decompress and play. A video game executable exists in a permanent frantic state of absolute panic. At any given microsecond, the runtime application must pull raw hardware inputs from a variety of peripherals, compute complex rigid body states, and flush millions of geometric instructions to the GPU, all while desperately trying to maintain a rock solid state execution window of exactly 16.67 milliseconds per frame. At the absolute center of this chaotic software ecosystem lies a single foundational piece of programmatic architecture. It's called the game loop. If this internal heartbeat hitches, drops data, or miscalculates for even a single millisecond, the physics of a virtual world break. Your control input lags, and your immersions instantly shatter. Let's step through the raw engine logic to see how these heartbeats functioned under the hood. Remember, we have been doing a series of videos concerning game engines and how video games were built, and the pioneers of the gaming industry, the game engines. So, like and subscribe to my channel. Let's get up to 1,000 subscribers. Thank you. At its most basic foundational layer, a game loop is an infinite non-blocking asynchronous while loop that initiates when the game engine starts up and breaks only when the execution process is terminated by the operating system. Asynchronous. In standard computer programming, code executes linearly and then stops, but a game engine must keep running regardless of whether the player is actively interacting with the hardware or standing completely still. To accomplish this, the infinite loop cycles through 3 structural phases during every single frame: processing input, updating the simulated game state, and rendering the final graphic output. Let's isolate the first phase. Input passing. At the beginning of the cycle, the engine queries the operating system's hardware abstraction layer, capturing raw telemetry from the keyboard, mouse, or console gamepad. This raw data is instantly processed, converted into semantic engine actions, and buffered into an input event queue, ensuring that no button press is missed during intense execution cycles. Once the input queue is populated, the engine advances into the most computationally demanding phase of the loop, the update state. This is where the virtual world actually processes logic. The engine passes the buffered input to individual gameplay system. If the jump action was flagged, the character's physics vector is modified by a gravitational coefficient. Simultaneously, collision detection algorithms like axis-aligned bounding boxes or complex rigid body matrices run across the environment to check if the player's bonding mesh interacts with a wall or floor. Artificial intelligence scripts evaluate the navigation mesh to compute pathfinding routes for enemies. Animation systems recalculate skeletal bone blend weights, and game state managers evaluate victory conditions. The critical architectural rule of the update phase is that it must operate completely independently of visual rendering. It is a pure mathematical computation of the world's state vectors in memory. Now that the engine has successfully recalculated the exact positioning and state of every single object in the virtual world for that frame, it moves to the final phase, the render phase. The engine collects the transformation matrices, material references, and skeletal scaling arrays, packing them into graphics draw calls. These instructions are flushed directly over PCIe bus to the graphics card. The GPU, that is the graphic processing unit, consumes these vector zeta buffers, processes them through the rasterization and pixel shader pipelines, applies lighting passes, and writes the final color values into the back buffer of your display configuration. Once the render commands are issued, the back buffer swaps to the front buffer, displaying the updated frame cleanly onto your monitor. The loop instantly resets, clearing temporary data buffer, and begins the exact same process all over again for the next frame. This sequence sounds remarkably simple, but it introduces a massive engineering obstacle: hardware synchronization. If you construct a native game loop that executes as fast as the host CPU can process instruction, the game will run at completely variable speeds depending on the machine's hardware. On an older office machine, the loop might cycle 30 times a second, or on a high-end liquid gaming rig, it might cycle 300 times a second. If your character movement code states move forward 5 units per loop cycle, the character will run 10 times faster on the modern PC, making the game completely unplayable. To solve this fundamental variance, engine architects implement a variable timestep metric known as delta time or delta time. Delta time tracks the exact fraction of second that elapsed between the start of the previous frame and the start of the current frame. By explicitly multiplying all physics calculations, transition matrices, and acceleration shifts by the delta scalar, game world movement automatically scale uniformly, ensuring identical execution speed regardless of whether your hardware is rendering at 30 frames per second or 300. As modern processors evolve to feature high core counts, the single classic threaded game loop reached its absolute scaling limits. Today's commercial engines like Unreal and Unity implement a highly advanced multi-threaded game loop architecture. The main gameplay thread drives the central state updates and input processing, while throwing heavy computational tasks like cloud physics, audio mixing, and AI pathfinding onto the worker thread via a distributed task graphics system. The render pipeline is completely isolated into its own dedicated render thread, which trails exactly one frame behind the main logic thread. This introducing an extra layer of complexity. Engine programmers must carefully implement thread locks, atomic variables, and double buffer data arrays to completely prevent data race conditions. Where one thread tries to read an object's position while another thread is halfway through modifying it. Managing this multi-threaded sync is one of the most complex challenges in modern low-level software engineering. Mastering the mechanics of the game loop is what separates a casual scriptwriter from a true engine architect. When you write code, you aren't just writing linear logic, you are composing instructions that must seamlessly align with a continuous, hyper-optimized hardware clock. If you are developing a project right now, do you manage your simulation state boundaries? Do you prepare the deterministic reliability of Unity's fixed update loop, or do you rely entirely on Godot's native physics process pipeline? Godot's native _physics process pipeline. Let's dive deep into the technical trade-offs in the comment section below. Be sure to hit that subscribe button to keep your software architecture knowledge razor sharp, and I'll see you in the next Ezugo Studios breakdown. Thanks for watching.